Welcome to 2.75x. And 275 is a class I've taught at MIT for many years, and a lot of these lecture notes have come from an earlier class, 2.007 I did, and all this stuff comes from humanity. I have been blessed over the years by working with some really bright people on designs of real machines and things who realize that one of the greatest joys is not only creating machines, but creating designers to make other machines. And then it just becomes a great big design party. That's what this whole class is about. And the way we've organized it is a series of modules, 1 through 12, maybe another 1 or 2 here and there. And it's all based on, if you do the reading beforehand and think about things, then when you listen to these lectures, and they're not really lectures, we're working together here on a problem, your brain will absorb the contents and filter it and put it in your own aspect of what you want to do. Because you probably are really psyched to learn this stuff so you can design your own gizmo for whatever reason you want to need it. Okay? And that is the key part of topic 1. Design is a passionate process. And we're going to go through that. And notice the motif here for the first part is we've got winter scenes, fall, summer, spring. Design is a process for all seasons. Okay, that's the theme here. And there is a rationale behind the theme in the shirts. A good designer is going to look in all the other places that most people will miss. Okay, so let's dive right in and go through this first series of slides, but we're going to do it in the context of something real. I happen to be passionate about drill presses. I'm passionate about a lot of things, but drill presses is my recent passion because in doing a project, I always seem to hurt myself a little bit because it's hard to fix your parts. You start drilling, it's not where you want, so you kind of crank it around. There's pieces like, and to save money, they put stankomatic mechanisms in. If you've got a part and you're drilling a hole here and you got to go to that hole and you've already clamped it down, you got to unclamp and whatnot, and if you try to move it, whoop, it swivels out of the way. So there's all kinds of frustration with drill presses. Not the least to mention that when it's running, if you put your finger in there, of course, that's bad. Oh, that's the wrong speed for drilling aluminum. See, now I got to wait for it to slow down. That's all right, we'll stop it. And to change the speed is a real pain. There's a whole bunch of real pains on here. And when I talk to some of my students and former students, they say, yeah, Alex, drill presses draw vacuum. And I don't mean to pull the chips out. We think we can come up with a better design for this stuff. And so we're going to use this as our theme machine throughout this class. It's everything designing a better drill press. And we'll do it in the context of you take the patterns that we're talking about. It's a better bicycle, a better milling machine, better solar power system. It's all a passionate process. You pick something that, oh, I want it better, and you apply your passion and your brain, good to go. Okay, diving in. Now, these notes you'll notice were written around a design contest. This class 270 was the original name and then became 2007 as it was expanded over the years at MIT. There's things like the first robotics contest that came out of that. Woody Flowers was a real big driving factor in taking 270 and moving it into the first robotics contest. So you say, what does a design contest with some kids designing machines to compete have to do with me learning, precision machine design or anything? The key is the score. In a design contest, you figure out to design the machine, what is the scoring algorithm? How do I maximize my points? It doesn't do any good to have the coolest machine on the planet if it doesn't score. It's the same thing in real design. When you're designing a drill press or a machine tool or a laptop, you got to figure out how to maximize the score. And is the score based on the accuracy in microns, on the load capacity in newtons, on the customer experience, which is a much harder thing to judge. But working with the people in your team, figure out how do we win? What is the score? Okay? In machine design, it's a little easier for us to do this often because it's based on the load capacity or the accuracy or the life. But any kind of design, that's what you do. Start with, how do I win? Or do good at least. For our drill press example, it's going to be on the precision of the mechanism in terms of how well does it repeat what we want it to do, and the scoring, and also in terms of the ergonomics, which again you'll see as we move on is a little harder to measure, but that'll be with user focus groups and things. Now, let's get ourselves in the mood, because we've all been involved in projects where it's like, heavy-headed in lecture, and you got a work assignment, and oh geez, all right, well, I got to pay the rent. I'll slog through this so I can pay the rent. Now, the key is get passionate. And as our buddy Ralph Waldo Emerson said, enthusiasm is one of the most powerful engines of success. When you do a thing, do it all you might. Put your soul into it. Stamp it with your personality. Be energetic, active. Wah! Get the energy going. Very, very important. So, like for example, I had a friend who graduated from MIT, happy advanced degree, and in his situation where he needed to live, home stuff, he couldn't get the job he wanted. He says, Alex, this is really bad. I can only get a job, selling retail. What's that got to do with engineering? I said, dude, show up a job with your notepad, and whenever you notice customers buying this cool stuff, make a note of it. When they come back, rah, this product, blah, 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 then you write it down and you start sketching a new idea. So whatever your job is, as a designer, you keep your eyes open and you notice what other people like and what they hate. And you come up with a new design, and then on the side, so you go start your own little design firm and company, you come out with a new product, then you can buy the firm that you were boring at and make it more exciting for the next guy. Okay? That's the goal. So even if you think your job is like boring, you can figure out how to make it really, really exciting. Okay? That's the first part of the game. Now, what are some words of wisdom to keep in mind? Because it's one thing to say, get excited, et cetera, et cetera. It's another thing, how do you actually do this? So to do that, we're going to teach you the 4-letter F word. Now, I know what you're all thinking, food. You may be thinking of the other 4-letter F word, free food. I'm thinking of the 4-letter F word, focus. And you say, what? That's 5 letters. Surprise, design is, people who are going to succeed at it don't always stay within the bounds. So they give you 4 letters, you only have 4 letters. What would I do if I had 5? Okay? But the key is focus. Figure out what that prize is, how you're going to win, and don't be too worried about things, because remember, 300,000 kilometers per second, it's the law, parentheses in a vacuum. Everything else, guidelines. So we'll start with a little bit of history. Mick Jagger and Keith Richards from the Rolling Stones, that some of you all may remember, or your parents when they read those books about dinosaurs to you to go to sleep at night. You can't always get what you want, but if you try sometimes, well, you might find you get what you need. So always try to work in the bounds of what's there, but not too hard. So if you find yourself being too restrained, remember, restraint is boring, passion is not having to be restrained, so look outside your bounds for what else is out there. And then there was this dude, Henry Maudsley. This is like, 300-400 years ago. And he's sometimes considered the father of modern machine tools. Because in the early 1700s, so 300 years ago, he came out with a lathe. There were lathes before, but they're made of wood. And they would wear out, and they weren't too strong. This cat said, I need something that doesn't wear out. There's this new stuff around called iron. And so he was one of the first dudes to actually make a cast iron lathe. He said very carefully, get a clear notion of what you desire to accomplish, then you will probably get it. Remember that score from earlier on? And notice what I'm doing here, and this is going to happen a lot through this class and through your life, okay? But I'm not going to keep reminding you all the time. I keep cycling back and going back to my random pile of Legos and pulling up ideas. Because design is not only this, it's that too, and get some of this. So you're always moving around. And if anybody out there does martial arts, you'll understand if you just sit there like this to fight, you usually get hit. So you got to keep moving around. Design is the same way. got to stay in motion. And that's also a lot more fun, because just to sit here like this is kind of boring. Okay? So we know what we want to do. Keep a sharp look on your materials. Get rid of every pound of material you can do without. Put yourself to the question, what business has it there? Because if it doesn't have any business doing there, and you're shipping it, you're losing money. Avoid complexities and make everything as simple as possible. This is KISS, right? Keep it super simple. Remember the gettability of parts. That's MISS. Make it super simple. All right? And this dude's in the 1700s, and the business schools are charging you for that right now. You don't need that. All you need is these, and a little bit of rock and roll. All right? Country music's pretty good. Actually, I like rap also. And classical, the moral of the story is diversity is how you really become a good designer in everything you do, from your team to your parts to your music. Always keep that brain flying around. Your head should be like a pinball machine when it has to be, and at other times, and we'll get back to that too. Now, notice earlier here I was kind of all over the place. And oh my goodness, blah! ADHD plus on steroids. Now, we're going to really focus, and we're going to go deterministic. Deterministic design means everything has a cost. Everything performs according to physics. There is no black magic here. In your personal life, you may have certain religious beliefs, and that can be very good for you. I'm sure of this, that if you have to pray to whoever you believe is the all-powerful to make your design work because you were too lazy to learn the material you needed to make it work, your prayers will not be answered. Okay? So remember, there's your personal life, and then there's, I was given the skills, the ability to do anything I want to do. I will use those skills I have to get it done, and the toolkit for doing that is physics, economics, history, language, communication. See, that's your toolkit. Use it. You want to make money too, in a good way. You want to have the economy, you want to employ people. Keep a close watch on the budgets. Time budget. It doesn't do you any good to take 5 years to get a product out the door that should have taken a year. You'll miss the boat. Money. Very few projects around say, oh, don't worry about the money. You can spend all you want. Yeah, no problem. Take as much as you want. Sure. Performance. There's a budget for the performance. If you want this machine to be able to drill a hole that's straight to 1/10 of a millimeter, there's rattle here, there's movement there, wiggle, 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 wiggle. How do you do the modeling of that? What's the physics of the mechanical system that will make it give you the accuracy you want from it? Okay, that's a budget. That's something called an error budget. You're going to have time budgets, money budgets, performance or error budgets. Your job as a designer is to keep track of all this stuff. Okay? Remember, get all the performance you can for the same cost. Stay nimble. Be ready to switch technology streams. They shouldn't be able to pin you down necessarily, because if your competition can track the trajectory you're doing, they can predict your next product, come out with it before you do. And now notice these curves here. Very important curves. We show figuratively cost on the vertical axis and performance on the horizontal axis. And this is a very key issue to deterministic design and any type of design. We have different technology curves, and I want you now at home to do the following real experiment. Draw a square. Okay, I'll draw a square. There's a square. Pretty good. Draw a square that is 10 centimeters by 10 centimeters, and the edges are orthogonal to within 1 degree. Oof. All right. And notice this earlier one took us what? 1.675 seconds. Now we'll do the new square according to what the guy with the formal voice told us to do. And that took about 5.2314 seconds. We'll have a note later about what it means in terms of precision. And that's actually resolution. So you can see here's this square that took about 3 to 4 times longer for me to draw. It's much better than that one. It took longer to get a little better. And you can do this experiment at home too. You were born. You can ask your parents about that. Guess what happens over here? Most of y'all hopefully are right about here. I have finite life. I have finite resources. Click. Oops! I just wasted 4 seconds of my life drawing a square. Click. So you see, time is money. You don't buy time. You can't buy it. Okay, now draw that same square, and I want the specification to be 10.00 centimeters on a side and an angularity, right, a perpendicularity, the base sides of 0.01 degrees. Okay, most people will never get there. You'll get all the way over here before you get there, and that's really a shame. So you jump technology curves from this early curve here, right, for example, where the cost is very low, and as I want more and more accuracy out of my square, it takes longer and longer and the time goes up. So the cost goes up and the performance is not any better. So I break out my laptop and I fire up a simple program like, in PowerPoint or something, you can drag a square to get this one, but it cost me time to turn on the laptop and do it. That's why this is this new curve. And then when you get the real high performance, and maybe I want this square, the size of this, to be proportional to another line. Oop, now I have to write an equation for the square. Now I have the cost that I got to pay for and open up, and it takes longer to open up, a parametric solid modeler. But look how far out in performance I can get for the cost. Okay? Now, notice this red line is called the disruptive technology here. This is what you got to be careful of. In the future, this is going to be square, square is there. Okay? So someone somewhere is going to implant electrodes in your head, but we're not there yet. Close. So this is what you need to always have imprinted in your mind in everything you do. How much time am I spending on this? What's the end game? When does it project due? And how do I get there using whatever the best technology is? Absolutely critical. Okay? And when you think about learning, the same thing applies. Figure out how you can get the most performance or learning for the least cost. How can I accomplish the job as fast as possible in the least amount of time with the best amount of output? And I hypothesize that you'll come back to, I'm so excited about this, passion. Okay, very important. Now, we just talked about deterministic design and thinking things through very carefully with the physics. And everything has a reason, and doing budgets. And we're going to dive in deeper into that stuff. Deterministic design, a very important part of thinking about things in a structured manner, is play. You say, how could play be anything to do about physics and numbers and determinism? And the reasoning is, most of y'all are probably humans. I know I am. And if you look at babies of humans, or actually of animals, they're tumbling, they're hanging around, and babies are always picking up stuff, And how many people it works? They'll chew on things, and you get the little twisted up pen caps. So we are tactile creatures. And I'm sure the brain dudes are going to figure out why neuron 47 talks to neuron 642 better if there was some touching going on. But the design, some people say, oh, serendipity. Oh, I was taking a shower and the idea came to my head. Or a higher power said, make it blue. I think the more simple reasoning is when you touch and you feel and you play, while you also have on that part of your brain that thinks about force equals mass times acceleration. The displacement of a spring is proportional to the force divided by the spring constant. So you overlay on your natural human actions of play the deep geek training you got. So take a look at my desk, all this stuff here. First of all, notice that this granite top, it's flat to only about 50 microns per half meter. In other words, this thing is flat to about 1 part in 2,000-ish, okay, 20,000. And why do I have a surface plate that's flat? For a conference table. This is a design group meeting. This is a meeting. This is what my table normally looks at. It's covered all kinds of stuff. Kinematic coupling elements, we'll go into that. Special little locking pins, hydrostatic bearings, trivet parts from the kitchen. Why? Because they interlock. And a lot of design can be done with patterns. We have 3 foamies that form a tetrahedron. How do you take 3 planes and form a tetrahedron? You've got to have 4 planes to form a tetrahedron. Try that trick. Okay, how do you take something that's flat, 3 of a plane, and make a tetrahedron, a 4-sided thing? Remember about focus, 4 letters versus 5. We've got these things, right? We're going to play bouncy rubber ball, right? Everybody knows what happens when a rubber ball bounces. Suck. Everybody knows what happens when a rubber ball bounces. Boing. That's just a materials change. So you can take 2 things that look alike. We'll get it later. And remember, when stuff breaks at home, that's a fantastic opportunity. But don't go necessarily break it at home front, because you can then take it apart and look and see how other geeks did stuff before. What works and what doesn't, okay? That's really a key. And when you surround your stuff with toys and gizmos, and check this out. This is by my friend Kent. It's an M&M machine. I'll get some M&Ms for later on when we get into the gear lecture. And as you turn it, it's got all kinds of mechanisms. Gears, it's got a Geneva mechanism, it's got cams, and it processes the M&Ms, which we'll get for the next time. We've got kinematic couplings. We've got massaging shapes. Very lightweight, strength by the multi-aspects of curvature. Okay? You populate yourself with the touches and toys and feels of whatever the area you're working in, and not in some other random place, but surround your environment with it so you absorb all the energies of tactilicity. Okay? Very important. Now, moving on. So you see play is important. It's wiring the brain. Now, analytical instinct. Instinct, what is that? Sometimes people say, how does that person know how to do that? They just designed it without actually writing down any equations or anything. I want to be like that. Math is hard. I just want to think poof, and have it. But what you'll find is people with time, they learn the math, they learn the physics, and they do the analysis over and over, and it imprints on the circuits. It's like doing push-ups, running to get ready for your race. You do the training and you wire yourself. And you got to learn to trust your thinking, trust your instincts. And if you don't have any instincts, you take that, aha, that's a weakness, I'm going to build that up, okay? Listen to your instincts. Be wild, creative, impulsive. But for every time you're wild, creative, impulsive, stop, think, what's the physics, okay? Be wild, crazy, and then focused and passionate. Reverse engineering. What does that mean? It means we all stand on the shoulders of giants who came before us. It means there are things that you can look at and you can say, well, that's wrong, that's wrong, that's wrong, that's wrong. But when they first came out with it, they were looking at the other product before that saying, that's wrong, that's wrong, that's wrong, let's do this, that, the other. And they came out with this beautiful product. And now I'm looking at this product, it was pretty good. But I say, well, I can do better. That's because I have a starting point. So reverse engineering is a really critical part of the design process. It's taking something that when it first probably came out was the best around thing out there, because there wasn't anything else out there as good. And it was fantastic. And then people use it and they learn, they observe, they touch, they feel, they do, and they figure out what's good and what's bad. You'll take it apart, you'll see why this gearbox is crunchy. Why is this rack here positioned the way it is? You look and you learn for what was done in the past. You apply your hierarchical methods of carefully taking things down, dissecting things, applying the physics. Remember, we're going to be doing a lot of this in the rest of the class. Okay? And that you use to start developing ideas. We're going to develop our ideas in terms of what are called strategies. This is the overall approach. Concepts. If you have a strategy, you're going to do what's now detailed concepts to implement it, breaking it down into modules and components. It's this deterministic thinking of slicing ever finer and finer, coarse to fine. Okay? That's what we're going to do. We're going to look from experience. If we don't have the experience, we're going to get it. Disruptive technologies. Look at the product in terms of evolving it, but also look at the product about, okay, what if I want to do something completely different? Maybe for drilling a hole, I don't actually want to use a solid mechanical bit. Maybe I want to drill a hole with electric sparks, with water jets, with lasers. You know, what does this machine do at what cost? What is the newest technology out there in a completely different field that maybe hasn't been harvested for this thing yet that I can actually apply also? Okay, so this is where you have to get really wild and be very careful of all the risk analysis, the money, the technology. And sometimes, if you're lucky, you come up with a totally different way of doing things. And we'll talk about that in one of our case studies when we get to structures, about a way we think we're going to be able to revolutionize wind energy. Now, a few more of this background in terms of overall approach to get your mind in the mode before we settle in on actually tackling this particular case study problem by way of example. Best engineering practice. Okay? It's very, very important that, remember, ounce of prevention is worth a pound of cure, or 62.5 grams of prevention worth a kilogram of cure. That's okay too. Depends what mode you want to be in. And best engineering practice says there's a reason for everything. Careful thought, following standards, random results are the results of random procedures, not some higher power is unhappy with you because your great-granduncle ran over somebody else's sheep. That's not important for design, okay? Follow what the customer needs are. Carefully look at failure. What is the cost of failure? How do I create a model for things, an analytical model where I can test drive with numbers? If I change this to this, how does that impact the result? Because you'd rather do it on the computer than in the marketplace. Okay? Schedules. You're born, something else. In here, you're going to be doing stuff. You have to design a new machine, you've got to get the machine to market. So start and end. In general, if you look here, we'll divide this up into 3 major chunks of activities. Our major chunks are going to be in roughly the first third of designing something between, hey, I need something, and look, we're shipping it, is what we call the ideation phase, or strategies and concepts are developed. You figure out what you're going to do and how basically you're going to approach and do it. And then the middle third is the detailed engineering and development. This is where a lot of analysis, selecting from the catalogs or creating your own machine elements, how the whole thing goes together. And then the last third, you integration and test. Test, and make sure it meets the specifications, okay? The class is kind of in the same way, actually. The first third is on the philosophy, overall approaches and things. The middle chunk going real deep on the power geeking. And the last part on we're going to bring it all together in the assemblage of our real machine, hopefully our better drill press. Okay? So remember this, and in your learning, okay, I've got 4 hours to complete module 1 or whatever it is. At the end of module 1, I got to take this test. I got to do this stuff. Okay, I'm going to take an hour to review all the material, be familiar with it. I'm going to take an hour to get some good fashion advice, and an hour to take that fashion advice and actually pull it all together and work on my detail machine. Okay? It works. This process works not just designing machines, but how you do learning and a lot of stuff in life. Remember risk management, stuff won't always work the way you think it works. There's this little thing called reality that happens to prop up now and then, which you didn't model for. So always ask yourself the question, what am I most unsure about? Where am I maybe asking for a little bit of luck? Or like, hold the handlebars real tight, going down the hill and hope you don't hit a rock. And prioritize these risks and have in mind, if you do hit a rock and you do go sailing over the handlebars, don't hit the tree. Try to give yourself a little bit of angular momentum as you leave the bicycle so then you can keep twisting and fall where you want to, as someone who has done that. Okay? Now, we're going to stop here. And our next module, we're going to then dive in depth of taking everything we learned in the first module and how we're going to apply it to this concept of strategies, concepts, components, and starting to get into the detail of the idea development. All right?